Welcome to this 22-minute webinar on Robot Programmer, a component of the 3D Experience Works manufacturing suite. In today's session, we'll provide a brief overview of several essential applications, offering a quick look at their enhanced functionalities. We'll begin with a part already designed in Solidworks. In this example, a standard MIG welded assembly. Let's dive in by uploading a welded assembly from Solidworks into Robot Programming Essentials using the 3D Experience platform. To get started, we will change the orientation of the welded assembly to Z-up. This is recommended for any models that will be used in the Robot Programming Essential application. Then it is time to save the file to the 3D Experience platform using Solidworks. To help organize our welded assembly, we are adding a bookmark, which makes it easy to retrieve as we move forward and keeps my project files in one place. During this save process, an important detail to check is the convert column, which provides feedback confirming that the file has been saved and is ready for downstream use. In addition, we keep an eye on the convert status by moving the column in the grid to the beginning. Once we see the green check mark, we can bring the model into the 3D Experience platform. We'll transition to the 3D Experience platform and launch the Robot Programming Essentials app to begin designing our robotic welding cell. The application opens in 3D simulation mode, so we'll switch to design mode to get started. First, we generate a resource by creating a manufacturing product container called a manufacturing cell and assigning it a name for easy identification. Then we add a manufacturing product within the cell to house our welded assembly. We'll bring in the Solidworks designed assembly using a simple drag and drop between apps. Once the assembly is open, inserting it into the manufacturing product is as easy as selecting it from the Open tab. The second step is to install the robot library. To do this, we access the 3D Experience web interface, then click on the Robot Programming Essentials app icon in the compass, and then select Install Optional Content Now. This installs the full library of industrial robots to our local install folder, a one-time setup. After installation, we can import our chosen robot into the manufacturing cell. The library features thousands of robots and cobots from leading industrial and collaborative robot manufacturers. For this project, we'll select a Fanuc ArcMate. Once imported, we create a bookmark for quick access in the future. Any robot imported into the 3D Experience platform becomes available for reuse by all users moving forward. The third step is to add the ArcMate robot to our manufacturing cell and position it. This process is straightforward. Simply drag and drop the robot from the bookmark. We place the robot at the origin point of the manufacturing cell for accurate alignment. To make the robot functional, we need to attach a tool, in this case, an arc welding torch. We start by opening the welding gun design in Solidworks, just like we did with the welded assembly, and save it to the platform. Using the drag and drop method, we bring the welding gun into 3D experience. Once imported, the tool needs to be configured to interact with the robot. In the Resource Creation tab, we select the Generator Resource function to define the welding gun as tool equipment. This step ensures the platform recognizes it as a usable tool. We then manage the tool's ports, adding a base port to the gun's root part for mounting and a tool center point TCP at the tip, where the mid-wire contacts the metal for welding. With these points defined, we drag and drop the welding gun from the bookmarks into the manufacturing cell. To attach it to the robot, we go to the Motion Controller tab and use the Set Tool function, assigning the robot as the parent and the welding gun as the child, allowing them to snap together in the correct position and orientation. Finally, we configure the Control Equipment option to complete the setup. Next, we position the welded assembly for the robot to access it for welding. Using the layout tools, we select the snap function and choose the assembly. To refine the placement, we add a local coordinate system to the top part of the assembly, allowing precise manipulation to position the assembly within the robot's reachable welding area. Now we're ready to program the robot by switching to 3D simulation. Previously, we worked in a static engineering model, but this step brings the robot to life, allowing it to move. We start by navigating to the Park tab to add the arc weld trajectories. Before setting the trajectories, we check that options to ensure the correct panels are visible and the necessary settings are enabled. With the options configured, we activate the resource. In this case, the robot directly from the 3D view or the resource tree, isolating it for focused programming. Next, we access the robot's profile page where we can explore various views, including text and graphics. Organizing the views by type and applying the layout to all containers makes it easier to manage and structure the programming environment. Next, we create the arc welding trajectories for the welded assembly. To do this, we select the robot and open the arc trajectory panel from the Park tab. This allows us to define the precise welding paths the robot will follow. Next, we verify the arc trajectory and ensure the approach angle is correct. The z-axis is crucial here as the positive z direction extends out from the torch, aligning with our tool center point for accurate welding. Next, we define the weld type, in this case, a standard weld along a specific section of the welded assembly. We then add a contour by selecting the appropriate geometry. In the Part tab, we choose to work with curves, though other options like surface or part intersections are available. To set the trajectory, we first select the initial curve by picking the relevant edge. Then we choose the base surface followed by the wall surface to complete the contour definition. Once these selections are made, we click OK to confirm the setup. At this stage, we have several options to refine the welding trajectory. We can set custom start and stop locations or let the system automatically calculate the seam length. For instance, setting the start position to 40 mm and the seam length to 50 mm updates the trajectory accordingly. Alternatively, if both values are set to 0, the system can auto-compute the same length. To visualize the robot or welding gun's path, we can toggle the eyeball icon. Enabling collision detection helps us check for potential collisions between the welding gun and the assembly, thus ensuring a safe operation. Additionally, we can set base and wall offsets to fine-tune the gun's position relative to the weld joint. Next, in the Orientation tab, we set the base and rake angles to control the welding torch's position, with the rake angle managing the push. If a collision is detected, we can either adjust the angle to avoid it or use the flare angle. In the Flare tab, we enable the flare distance and set the angle to 50 mm, applying the same adjustment for the end weld. After that, we move to the Safe Path tab, where we define a safe approach and retract position to ensure the robot can move to and from the weld area without interference. To speed up the programming process, we can replicate the parameters from the first weld to create the remaining welds, resulting in 3 distinct welds. In the Behaviors tab, we'll see welds 1, 2, and 3 listed. Once the welds are set up, we can generate a tool cloud to assist in designing the holding fixture. This is done through the Export Tool Cloud option in the Setup tab. By selecting the target welds in the tool, the platform generates a tool cloud which can then be imported into Solidworks to guide the fixture design. Before generating the robot program, we need to add a few robot-specific commands tailored for offline programming, or OLP, with the Fanuc ArcMate robot. These commands ensure the program is compatible with the robot's capabilities and properly executes the welding tasks. To refine the arc welding process, we need to adjust key settings like weld schedules and applicative profiles for MIG welding. In the Setup tab, under the New Tools Profile flyout menu, we'll find the Applicative Profiles function. Selecting the robot opens the Applicative Profile Management panel, where we can create profiles tailored to the fanning controller. We'll create a new arc welding profile, setting the approach weld speed to 10 millimeters per second. For the arc in profile, we'll also set the weld speed to 10 millimeters per second at a fill time of 0.5 seconds to complete the weld smoothly. Now we configure the start and NTP arc commands by linking them into an arc profile. In the Arc tab, we use the Create Arc Profile function. Selecting the robot opens the Create Arc Profile panel, where we add the applicative profiles to each section. Here we can set parameters like delay time and weld speed for both the start and end profiles, ensuring precise control over the welding process. Next, we create the arc welding task by navigating to the Programming tab and selecting the Generate Robot Task function. This opens the Create Operation panel, where we choose the arc welding trajectories to include in the program. Once the task is created, we can run the robot welding simulation by clicking the play icon in the center of the compass. The simulation follows all the applicative settings we configured, showing the robot moving through each trajectory with the correct dwell time and weld speed. Next, we refine the program by selecting the Teach function in the Programming tab. This opens the Teach panel, allowing us to step through each arc operation and adjust position types and speeds. We can view and modify linear and joint moves, setting specific motion speeds. We can also sort targets by type like approach, arc start, arc weld, and depart, and assign distinct speeds for each. For instance, we might set all linear moves with a motion profile of 1500 and an accuracy profile of 75 for continuous movement. After fine-tuning each motion type, we run the finalized program by clicking the play button to see the robot execute the optimized welding sequence. Finally, to download the program, we generate the robot's native language. In the Analysis and Output tab, we select the Generate Robot Program function, which opens the Create Industrial Robot Program panel. Before downloading, we ensure the robot translator is imported. Although we've already imported the Fanuc translator, we will still walk through the steps here. So we will navigate to the installation directory and select the Fanuc robot translator. With the translator ready, we return to the Create Industrial Robot Program panel. Choose the controller type, in this case the R30IB, and select the robot task. After completing these steps, the program is generated in LS format, ready for deployment to the robot. If you have any questions or would like to explore more about the robot programming role we discussed, feel free to reach out to your local reseller. You can also join the Delmia Robotics community to connect with us and other users globally. Thank you for attending our session and have a wonderful day.